Shall we start? Okay, good to see you all. This is Introduction to Quantum Computing class. Today we're going to introduce some of the brief overview of the course, and we're going to cover the early material of the quantum computing, which is the vector and vector spaces. So for the first 15 minutes, I'm going to introduce what the course is about and how we're going to operate the course, and also um, some necessary links and information about the course. So before I start, is there anyone who didn't register but still here? Okay, so if you go to the LMS, then I posted on one announcement, which is just a simple link. There's a link to our My Notion site, and it contains all the information you need. And the slides that we're going to use is also posted on that Notion site. Throughout the semester, we're not going to use LMS much. It's going to be only for posting your personal score if it's necessary. Other than that, you can only go to the Notion site. Just bookmark your Notions and all the information will be there. Okay, so this is the quantum computing. My name is Hyo-Sang Kang, and my office is in the G floor at G11. My office hour is not fixed. So anytime, I mean, every semester, I cannot fix the office hour because you guys all have different schedule. So I'm basically free every time. So if you want to meet me, you can make an appointment by sending email. And the class time in classrooms are here. So this is the important part, the grading component. The grading consists of three components. The first one is in-class participation. So it basically means that you have to actively engage our class discussions, because I'm going to encourage lots of discussion throughout the semester. So there are, of course, many things to talk about. But instead of me talking all the time and you listen all the time, it's important that you can express your thinking and understanding in your own language after I told you about the basic information about quantum computing, because it's going to be a little bit different from what you conventionally learn about in mathematics or physics or in computer science. I learned personally, I self-taught this quantum computing a few years ago, and I found it's very weird at the beginning, because the how it works is quite different from other conventional traditional field. So anyway, so I encourage you to speak a lot, and that's going to be part of your in-class activities in the grading component. And the second component of your grade is a project. So it consists 40% of your grade. So there are going to be two projects basically, and project should be done in groups. So if you want to keep the group for two consecutive projects, you can do so, or I encourage you to change the group. So first project is, of course, it's worth 20% of your grade, about making a quantum simulator. So I'm going to introduce one or two types of quantum simulator that is out there, available, and sometimes free. What we are going to do in this project is not to reverse engineer or not to just mimicking their simulator, but instead we are going to make our own and somehow improve what is missing in public quantum simulator. and so that you can get the better understanding how quantum computing works. Okay, so that's the first half of that's for the first half of our semester. And the second project is about quantum algorithm, but it's not really about algorithm, but it's because it's really hard to get to create a genuinely new quantum algorithm. If you do so, you don't have to be here. So I'm not expecting you to create a genuinely new algorithm, but I'm asking you to find out what kind of algorithm out there, or if it's an existing one, an old one, find out how could you implement that algorithm into another situation, for example, in the research area that you're interested in, or in a business model or something like that. So that's the project 2. And the third component of the grade is the report. So this is summarizing how you have done in the group, done in the projects, and explaining the background theories and so on. I'm not expecting to see a long report, though you can do so if you're willing to transform your report into another paper. If you want, you can put as much effort you can put into the report. But I'm not expecting that much. I'm just expecting the brief and concise and concrete report on what you have done. And project should be done in groups, but report could be done individually. Of course, you can write one report in one group, but you can still separate your group into small subgroups and then write separate report on the same project outcome, because each one could have a different opinion about how you look at your output or the product. So you can write your own report on the product that you made in groups, but you can also work in teams. And also, I'm going to give a format, but if you don't want to follow that format, it's fine to have yours. But at least I encourage you to write in a file format of Markdown, so that I can have a same formatting of everyone in here. And grade scale. So this is how I give a grade every semester, every class. So if you get the scores 90 or more, then you get A plus. And this is after rounding up the decimal points. And there are, it doesn't really happen in this kind of courses, but I give a grade F if you don't submit the report or don't participate in any of this project. But this is a senior course, so I'm not expecting to see this kind of thing happens. But sometimes it happens, so I'm just putting it here. And here's the weekly schedule. We have 16 weeks, and I'm just going to go through all the keywords. It also covers what you're going to learn throughout the semester. So first week, we're going to talk about the qubits, which is the basic concepts of the quantum information. And second week, we're going to talk about quantum gates, which is basically similar to the whenever or like and or not gate in the classical computer, but in a different sense in the quantum computer. And the third week, we're going to talk about quantum entanglement, which is the core idea of how quantum computing works. And the fourth week, we're going to talk about quantum circuit, which is the basic for developing an algorithm or designing a quantum computer. And there are lots of holidays. And also in the week 5, I'm not sure whether this is because of my personal schedule. I'm not sure whether it's going to be available or not. So I'll notice when the day comes. For now, I have a schedule here, so I'm just putting it as a TBA. Okay, so until the week 5, we're just covering the basic materials. So since from the week 6, we're going to cover quantum algorithms. So on the week 6, we're going to cover early quantum algorithm, which is just it's not a practical algorithm, but just algorithm that the that almost all quantum algorithms are based on theoretically. And on the week 7, we're going to prepare to explain about the Shor's algorithm. So you probably heard about Shor's algorithm in many places, and that requires lots of background knowledge, including number theory. So on the 7th week, we're going to talk about the quantum Fourier transform, and after the midterm, yeah, I forgot to mention this, week 8. So as I said, there's two projects. The first project should be presented on the week 8. So probably by the end of week 5, you should be able to know what the quantum circuits are and how you could design a quantum circuit. So that means you have a better understanding of how quantum simulator should look like, and also how your outcome or your product should be look like. So you have 2 weeks for designing your own quantum simulator in group. And then in week 8, you're going to present your work. And in the week 9, I found that it's Hangul Day on the first class. So I'm going to spend one class for explaining the BB84, which is the quantum key distribution protocol. And from week 10, we're going to start the basic theory on the Shor's algorithm, and then we'll keep adding on from there. And then, until the week 13, we're gonna talk about how quantum algorithm works. And from week 14, there's a whole new different topic starts, and it's I cannot cover this quantum error correction stuff in 2 weeks, but I'm just going to introduce the very basic theory on the quantum error correction, and also currently the most hot topics on the quantum error correction, which is the surface code at the end of the semester. And of course, the final week is devoted for the presentation of your second project. So that's basically how we run the class. I know that there's 31, so maybe 32 by now, registered class student. And as I've shown before, this is a table for your group. It's not the group for entire semester, it's only for this course and this class, today's class. So I'm going to randomly generate groups, each class for the first few weeks, so that you can get to know each other until you have to fix your group member for the first project. So you're already sitting in whichever seat you want here, but I want you to move your seat according to the group number that you're assigned. So for example, the people on one row is in the same group. So these are 4 members here, say 4 members. There are total 8 groups. So I have number up to 10, but you can find your numbers somewhere except for these 2. Yeah. So please move your seat next to the number that you're assigned here right now, so that you know who your members are. Again, this is not the group for entire semester, only for today, so you don't have to worry about splitting with your friends. Okay. If you don't have rooms, then you can move a little bit. So maybe the group 8 can be a little bit moved to the left here, to the left. Yeah. What's your group number? 1? 1. Come here. You don't have to sit in the same row. You can sit in front and back. Okay. In the meantime, if you have do you have any questions about the course? The information I just gave you. No? Okay. Yes. Well, I cannot stop you speaking in Korean, but I encourage you to speak in English. So there are two reasons, because it's this is a very safe environment that you can practice your speaking, English speaking, right? So no one's gonna judge you. No one's gonna say anything about your pronunciation, grammar, anything, and even apply to me myself. So yeah, if you I just encourage you to speak in English. I'll just take time, and even if you're struggling making a sentence, that's perfectly normal. It's one of the process you have to go through whenever you start to speaking in English. You have to think about how you have to lay out your sentence, and then what you have to ask, and what's the thing that you want to ask, and so on. So yeah. So it's okay to speak in Korean, but I'll answer in English, and I'll also gradually you guys to ask in Korean, ask in English, and also whenever I ask you to discuss with your group members, it means that you have to discuss in English. Okay. Any other questions? Yes. It's okay because it's only a one time group, so it's not your permanent group. So your group is not for doing some work together. I mean, currently I'm assigning the group so that you guys can know as many people as possible. Okay, so until by the second or third week, you will probably have grouped with at least 10 students here. So now then you know what these students or what your friends are, how they're communicating, and you probably find your right partner to work with, right? So then you can make your own group by selecting or gathering friends together so that you can get the project done. Yeah. So it's okay not having a partner in one day. If you have one person in one group, if that happens, then I'll assign you in a different group. Any other questions? Okay, so let's talk about. I mean, if you have any questions, let me know anytime. You can pause me anytime, ask any questions. Yes. So, by the way, well, I can explain this later, but let me tell you right now briefly. So, if you go to the Notion site, Notion page through the LMS site, you can see some links here. Oh. I think there was something more. There were something more. I think I deleted. Oh, okay. So I think I deleted accidentally here. So what I intended here is not this one. Okay. So every time I'm going to create a link for live share of uh, work. So delete and delete. Okay, so here we have links to our lecture notes, lecture videos, which are going to be posted on the YouTube and the GitHub site. If you go to the GitHub, you will see lots of repository for every week. So every week I'm going to create a repository containing the file of yours. So these files are made from your student ID based on your registration. And if you go to this file, you can find the date and your name. So go to the file. I mean, not here. I'll tell you right after I explain this. And whatever we discussed in our class should be posted on this file so that I can collect all the work you've done throughout the semester at the end of semester, so that this count as the in-class activity component of your grade. So how do you access this file? Of course, this GitHub shows you what's the content. You can access this file through our live share link. So just before this class, I tried the Replit site as a place where you can edit your file, but Replit only allows 3 collaborators, so I decided to use LiveShare. So LiveShare directly connected to my VS Code right now here. So if you click on the LiveShare, I think maybe you have to log in order to edit. I'm not sure, but if you click this, then the window pops up and shows my screen of VS Code. So you can, I'm pretty sure you can edit. If you can't, let me know later. And then you can find your name, student ID file here, and then you can start writing something. So what do you have to write? You have to write the thing that we are supposed to discuss for every class. So for example, we're going to discuss about the vector field, vectors and vector spaces. Then after I give a lecture briefly, I'll ask you about some topics and what do you think about this? How would you think about this? And then you have to discuss within your group, and then your conclusion must go into this file. So that's your work. That's your activity. All right. So we can start from vector spaces, right? So is there any other questions that I miss? And there's no tendency, okay? So I'm not taking a tendency here. I'm not calling your names. So, all right. So we have to start from the very basics of vector space vectors, because later you will see that the qubits are represented by vectors. So it's not simple vector because normally you make a visualization of the vectors as an arrow, and that arrow is usually represents the real vectors. But here, when we're talking about quantum computing, we're talking about the complex vectors. So let's talk about the complex numbers. So complex number is of this form. So x plus y I. Here, x and y are the real numbers. Even if it's the trivial material, just take it as a review. And I is the imaginary number, which takes, if you take the square, then it becomes -1. Of course, there's no such real number whose square is -1. That's why it's called imaginary. And there are operations that you can do on these complex numbers, addition and multiplication, just like real numbers. If you want to add two complex number, you can do so by combining the real parts and imaginary parts. The real parts are x parts here. This is called the real parts. And this is imaginary part. By the way, so x here is sometimes denoted as real part of z, and y is denoted by imaginary part of z. Okay, and you can also take a multiplication between two complex numbers. So this is the final form of the multiplication of z1 and z2, but the process in between is the following. So you're just doing exactly what you're supposed to do, just as real number, like this, and you're distributing all these terms. So for example, I want to distribute x2 terms, x1, x2 plus y1, i, x2, and then you distribute y2i terms on the left, so you get x1, y2i, y1i, y2i. Now, when you take a multiplication of real numbers and imaginary number I, you can switch the orders. So here x1, x2 is fine, but y1i, y2, you can switch the order of I and x2, so you can write it as y1, x2i. Okay? And here, that's fine. I is at the end. But here, you can switch the order of I and y2 so that you can write it as y1, y2, I squared. So that means minus y1, y2. So that's why you get these two terms. Okay, so, and then there are more operations. One is the conjugation and the other is the size of complex number. The conjugation is simply taking the minus to the imaginary part. So if you pictorize your vectors, pictorize your complex number in the complex plane, then it's simply reflecting the points throughout the x-axis. And the size of the complex number is the square root of the sum of squares of real part and imaginary part. So this is simply almost same as the size of a vector whose components are x and y. And well, let's look at this example. It's a simple example. So if you have this z1 and z2, then you can compute your, first of all, size of z1 and the sum of z1 and z2 and the complex multiplication of z1 and z2. So I just lay out all the details here. So is it familiar? Not hard, right? So pretty sure it's trivial stuff. And here is one more thing that reminds you what you learned a long time ago. So here's the polar form of complex number. So you can either express your complex number in x plus yi form, or you can express in exponential form. So r here is the real number, and theta is also real. And with this formula that exponential theta I is cosine theta plus sine theta I, you can plug that in here in this place so that you can always write your complex number in this form. So it's basically same as polar coordinate of two-dimensional point. So xy can be represented by polar coordinate r and theta. So your complex number z, it can be mapped by the point x comma y. You can also have a polar coordinate of that point. This theta r is that polar coordinate of the point represented by the vector complex number. Now, what's good about having exponential function as a way of describing the complex number is that you can have these two identities here. First of all, you can add two complex number and take the exponential. You can still do that, and that is same as this multiple of exponential. It's same as the exponential function on the real numbers, right? But you can check this easily why this is true. So let's take let's say z1 is x1 plus y1i, and z2 is x2 plus y2i, and plug that in here. So you get x1, x2 plus y1, y2i, right? So these two, well, I have to still explain the reason here, but can be split into multiple of exponential x1 plus x2 times exponential y1, y2 of I. And then now you can further represent your exponential x1 plus x2 as exponential x1 times exponential x2. And then you can do the same thing for the rest of the parts so that you get these two multiple here. And you can also multiply two complex number represented in polar form as follow. So this is exactly the same as this polar Euler's formula here. So this is just the basic stuff that we already know. I'm just reviewing stuff, but if you're not comfortable, let me know anytime. We can do some examples. Now, as I said, we're going to talk about the complex vectors and complex vector space all the times. Okay, so quantum computing is no longer about the real numbers. It's always about the complex numbers. So you have to get familiar with the complex vector space and complex vectors. So what is the complex vectors and complex vector space? So these are the vector spaces, basically, only differ by the real vector space with a scalar. So the scalar, the number, is not real number. It's a complex number. However, the basic properties are the same that you learn in the linear algebra course, probably. Any two vectors can be added together, and this addition satisfies the usual properties of addition. For example, if you're adding 3 or more vectors, it doesn't matter which addition you do the first, and also you can switch the order of addition. And you can also have a zero vector, which means that all the components are zero, but in the more abstract sense, it means that it's an identity in the addition operator. That means if you add zero vector to any vectors, it doesn't change the vectors. And once you have a zero vector, you can think about the inverse vector, which means that you just take the minus of it, so that if you add with the original vector, you get zero vector. That's the zero vector. And again, you can take the scalar multiplication, and here the scalar k is always considered to be complex number, not the real number anymore. Okay? So here's the example of a complex vectors and complex vector space. The complex number and a set of complex numbers are the complex vectors and complex vector space itself. So how do you prove this? So first of all, you can have a vector addition as addition of two complex numbers. Okay, so number is considered as the vectors, okay, here. And scalar multiplication, so simply you can multiply a complex number c with another complex number z, but here z is considered to be the vector and c is considered to be scalar. And zero vector is just a zero number in complex number. And inverse is supposed to be the minus z. And here's more interesting thing. We're not going to talk about one-dimensional complex vector space anymore. We always talk about two or more dimensional complex vector space. Actually, it's even dimensional vector space that we are going to talk about for the qubits and quantum computing. So here is the example of two-dimensional complex vector space. So it consists of pairs of complex numbers, Z1 and Z2. Okay? So vector addition is component-wise addition, and scalar multiplication is multiplying the constant C on every component. Okay? And zero vectors consist of zero numbers, and inverse are putting minuses on every component. Simple, right? Now, when you talk about the complex vector space, you no longer able to visualize this vector in any of this picture, because now we are living in a four-dimensional real dimensional space. You cannot draw the four-dimensional space, right? And we can also talk about inner product. So in the real vector space, the usual inner product we're talking about is the product of each component and sum them up, right? So it's a Euclidean inner product. But when you're talking about the complex vector space, if you do the same thing as if you did the real vector space, you no longer get the real number as a product, as a result of the inner product. For example, if you have Z1 and x1 plus y, sorry, not this one. Z1, Z2, and W1 and W2 as example of the two-dimensional complex vectors. And let's say you try to do the same thing as if you've done in the real vector space. So you're trying to multiply the first component and second component together and add them up. That does not necessarily always the real number. So what we are requiring for inner product, no matter what the vector space are, the inner product always are required to be the real number. So that's not the way we are defining the inner product. We are defining an inner product in the following way. So this is general definition of inner product, but this is how you define inner product in real examples. So here, I'm not taking the multiplication between two complex numbers. I'm taking a different symbol. It's an empty circle representing the inner product. So it's not Z times W. It's that inner product with W. So it's given by Z bar W. And but actually I made a mistake here. So what I'm expecting here is I'm trying to take Z1 and Z2, the same vectors. So I'm trying to make these two, the inner product of itself, as the real number. Okay. So here, this is an example of how you take the inner product on one-dimensional complex vector space. So you're taking Z conjugate and multiply with W. By doing so, what happens when you take the inner product of itself? So that is Z bar times Z. So what was it? It's x squared plus y squared. It's always R, right? And always it's positive, or could be zero if it's a zero vector. And then you get the desired property of inner product. And when you want to define the inner product on two-dimensional vector space, for example, in C2, that's how you define it. But simply, it's a generalization of the inner product on the one-dimensional vector space. Okay, well, this is also important. I'm not just telling you the completely mathematical theory. So it's relevant, tightly relevant to our quantum computing here. Now, let's talk about the linear combination. And so basically, it's combining all of the vector addition and scalar multiplication. So you take n number of vectors, and then you take the scalar multiplication on each vectors, and then add them up. What does it mean by linear independence? If you take n vectors, u1 to un, and you take the linear combination, and suppose that it happens to be zero vectors, And only way that you can make this linear combination equals to 0 vector is when you have all the coefficient equals to 0, then you can call this set of vectors as a linear independent vectors. Okay, that means basically these vectors are directing in all different directions. No 2 or no 3 vectors are linearly combined to make another vector in the set. These are directing all different dimensions. So for example, let's talk about this one after the lecture together. So we're going to decide or determine whether these 2 vectors or 3 vectors are linearly independent or not. Again, we're not talking about the real vectors. We're talking about the complex vectors. So here, C1 to Cn's are complex numbers, not real numbers. So we're going to revisit this example after finishing my lecture. So before then, I want to mention about the basis. Again, whenever you have a vector space, you want to express any vector in that vector space as a linear combination of some set of vectors. So which vector you have to choose, that is the basis. So basis is a set of vectors that you can create any vector in the vector space, and also that linear combination is always unique, which means that the set of vectors is linearly independent. Okay? So let me emphasize again. So if I have V as a linear combination of this U1 to UN basis vectors, this is unique. There's no other way to combine these U1 to UN vectors to make the same vector. There's only one way you can do this. So here's another example. Let's check whether the set of U1, U2 provided here is the basis. So again, you can check whether this is a basis or not, but I'm not telling you that this is the unique basis. Basis is always not unique. You can have infinitely many bases, but I'm just telling you, you can check whether this U1, U2 makes a basis of C2. So here's another one. If you have 2 vectors and take the inner product to be 0, then these 2 vectors are called orthogonal. That means it's perpendicular. So if you're looking at the real vectors, it means clear that you have 2 vectors are perpendicular. But if you have, complex vectors, and if the vectors are 2-dimensional complex vectors, then you're looking at like 4-dimensional real vectors, and it's not clear what that means. So whenever you talk about the orthogonality, you always think about it as in terms of inner product, not geometrically. Okay. And we talked about the basis, but once you have a basis, if you remember the Gram-Schmidt process, you always can derive an orthonormal basis. So that means all the element in the basis set is orthogonal each other, and once you get this orthogonality on mutual orthogonality, then you can always normalize all the elements to have length 1 for all vectors. So then this basis is called orthonormal basis. So you can see, as an example, these 2 vectors consists of orthonormal basis of C2. You can check whether these 2 are linearly independent, and whether these 2 vectors are normalized, which means that it has a length 1, and also these 2 vectors are orthogonal each other. All right, well, that's the short introduction to the vector space. We didn't cover about the qubit, but this basic material will be used in understanding of qubit next time. So it's not the end of the class. I'm going to spend the rest of the time so that you can discuss about the topics. For now, I'm not going to give the topic right now, but the examples I just covered. So how about we start from this example? We have 3 examples that I introduced. So let's try to answer these questions. So check if the following sets of vectors are linearly independent. That's the first. And if it's not, find non-trivial linear combination that gives the 0 vectors. So check if if it's linearly independent, prove it. If it's not, provide a counterexample. And do the same thing for the second set of vectors. So I'll give you about 2 or 3 minutes to think about shortly on your own, and then what I'm expecting, what I'm going to ask you is to talk to your friends right next to you, sitting right next to you, and then, or if you're a group of 3, you can work all in three people can work together, and then you can talk within the group, and compare your answers. And then after discussion is over, I'm going to ask random groups, what was your conclusion and how did you come up with that answer? Okay, so before we start, is there any questions? Is there any questions that we just covered? No? Okay. So take your time for about 2 minutes to think about these 2 questions, and then I'll tell you what to do next. Oh, we're not doing this one. We're doing this one. Okay, well, it's time to talk about your thinking, not your answer, with your friends. So just turn yourself around to face your partner right next to you, or 3 of us, 3 of you, so that you just present your thoughts. So whatever you thought about it, and if you came up with an answer already, you can lay out your answer. But if you don't, just think about just express your thoughts. Yes. Yes.
Even in room meet
Yes.
discussion. Okay. these two vectors are not linearly independent, then when I multiply here to 2/2i, and also multiply 2/2i, then this should be same with this when multiplying this, but it isn't same. So these two vectors are linearly independent.
Okay, so if you're done talking with your partner, now it's time to talk in groups. So if you're already talking in groups, that's fine. But if you're a group of 4, then it's time to gather all 4 people around and then talk together. So here's the group I mentioned before. Where is it? So here, this group, if you look at the group order here, so I'm going to assign the first person on each column, first person on each row as a leader. So I'm going to ask him, as this person, to about the answers that your group came up with. Okay. So I'm not asking you to have concrete numbers or values here. So I will ask the idea what you discussed within the group. Okay.
A, B, C를 모르는데 이게 아, 네. 자원 관련해서 이제 지역권이가 원래 명사일 수 없는데 제 생각에는 이제 포수가 아닌 들어가가지고 이렇게 넣어서 그래서 그 형식이 되면 영역밖에 그렇게 이제
Yes.
First column,
First column is the leader.
bigger,
Yes.
not doing
Not doing what?
just leading the
Yeah, you can lead the discussion.
한 사람 없어.
Okay. Then the second person is the leader. Okay, how about group 3? Where is group 3? 이인규. Who's 이인규? You're the 인규. Okay, so what was your conclusion in your group? Oh, so you don't have conclusion for the first one? Determinant of what? Did you combine these two vectors as a 2 by 2 matrix? Okay, you compute the determinant. Okay, so it's not 0. So therefore, what independent. Independent or dependent? Independent. Okay, yes. Determinant at 0 means the dependent. Okay. So you didn't come up with the conclusion on the second part. Okay, so dimension is 2, but we have 3 vectors, therefore it must be linearly dependent. Okay, but you didn't find the non-trivial example of finding the linear combination equals to 0. Okay, anyone else have different approach for these two questions? How about group 4? Jung Eun-ho? Who's Jung Eun-ho? No? Kwon Do-yeon? Yes. So how did you come up with the answers? So is your conclusion same as the conclusion of group 3? So first one is linearly independent, second is dependent. Or is did you came up with the same conclusion? Okay, so how did you conclude first one is linearly independent? C, what is C here? C is a complex number. Yes. Okay, so you thought, you tried to solve this equation, assuming C1, C2s are real numbers. Okay, so C1, C2s are complex numbers. So did you conclude the second part? Not yet? Okay, so how about group 5? Yeah, group 5. Kibom? Not here? Absent? What's your name? Cheon? Okay. So how did you come up with a conclusion? The same conclusion? Yes. Right. So how did you come up with the first one? You solved for the equation. Okay. Assuming now in this case, C1, C2 are a complex number. Okay, so good job. So and then did the same for 2? Two equations. Yes, right, yes. Okay. So, right, so you want, if you try to solve this equation, basically you have 3 unknown, but 2 equations, right? That means you either have infinitely many or none. Right? So, yeah, good job. So there are 2 different ways for so far to conclude linear independence and dependence. One is that you just count the number of vectors, since it's 2. Or in this case, another one. So either you take the determinant and see the determinant, the value of determinant is whether 0 or not, or you just count the number of vectors. You have 3 vectors in 2-dimensional vectors. That means it has to be dependent. Any other method that you used here? Yes, group 2. The first one? RREF, I see. Okay, so that's basically same as computing the determinant. Yeah, that's right. Anyone else for the first part? So I heard interesting reason why you come up with the conclusion. Yes, yes.
I forget about many parts of linear algebra, but I think in vector V, we can multiply start from 2 to root 2i. We can multiply root 2 over 2i.
Right.
Then if these two vectors are not linearly dependent, if we multiply same number
On here.
vector,
All right. Yes.
then the result should be minus I,
Right.
but it isn't. So I think the two vectors are linearly independent.
Right. So you're basically looking at the ratio between components on these two vectors. If it's a linearly dependent, that should be the ratio should be the same. But if it's not, then it's linearly independent. So yeah, that's another way you can check whether two vectors are linearly dependent or not. If they are dependent, then one is the multiple of another, right? So multiple of another means that these two components have the same ratio. Basically, that's the idea. So, well, this is the first day of our first class. So I'll just let you know how I'm going to check your activities. Go to the Notion site and click the live share. See if it can access to my Visual Studio Code. So click live share on the Notion site. It will pop out the window that shows the screen. It's actually not exactly the same screen. I think you can navigate on your own. So let me close out. Oh, it's because they're doing the same thing. Okay, so yeah, so I can see some of you. So what happens if I close this window? Does it close for everyone? So if I close this, so I thought even if I close some windows, it doesn't close the window on your side. If I close the window, does it close on your side? What happens here? So okay, so Kim Siwon, where is Kim Siwon? Yeah. So I'm going to close your file. Does it close on your side? No? Still open? Okay, so I can close it, right? Okay, so I'm going to save it before I close it. There's so many files are opened here. So yeah, I think you already know what's going on here. So I'm expecting you to write what you have thought about the questions or what you discussed within your group. So for example, you can use the math formula here freely. So for example, if I, let's see, open up my own MD file here. Now, there's some title here. So now I have to talk about, okay, so U equals to, so do you know how to write the math formula in LaTeX? So if you heard about the LaTeX format, the Markdown supports the LaTeX formula. So for example, if I, what was the formula here? Yeah, 1 minus SQRT 3I, comma, minus I like this. And if you want to see the printed version of this text, then it automatically converts into math formula. So you can use your math formula in your writing. So if you want to talk about how you thought about the questions, and question involves, or your answer involves some math formula, use the formula in LaTeX format. So, well, that's so this is an example how you should write. So let me go briefly about what I would like to see here. So first of all, let's say how to check the linear independency between two vectors. So first one already discussed, that you take the determinant to two-dimensional vector, determinant of matrix U1, U2. So here you can see that my formula is basically converted into the nice formula here as I write. And then if the determinant is non-zero, then two vectors U1, U2 are linearly independent. That's the first method you can check. And second method is just solve the system of equation of C1 U1 plus C2 U2. That's the second method. Or check if the scalar, if U2 is a scalar multiple of U1. So that's basically the answer from group 1. So you take the ratio between two vectors, components of two vectors. That's the same as checking if one vector is scalar multiple of another. Okay? So this basically just summarizing what you have heard or what you have thought in the group and so on. So I'm expecting you to write this. And well, of course, if you don't have time, you can keep writing after the class. And I'm going to open up, not sure how long can I open this up, but at least I'm going to open up until like 4 p.m. Okay, so because this is a live share, which basically shares my side of VS Code, I cannot open up. I think if I close my laptop, it immediately closes off. So I cannot open up for longer than that. So anyway, that's how you could do it. Yeah, don't copy and paste here, sorry. You don't have to copy paste. All right, let's talk about other ones. Any comments that you want to add on this part? No? Okay. So how about well, that's the same simple one. Since it's simple, let's do it. So let's do this one. Example. Show that the following vectors are forms a basis for two-dimensional complex vector space. So same thing here. You can think for about 1 or 2 minutes, and then you can talk to your partner right next to you, and then you can talk within the group. So this is a complex vector. I'm sorry for this. So you cannot draw it like this. It's not a two-dimensional real vector. Yes.
Can I take color from the complex section too?
Complex what?
Complex part. Like C1 for like I or X plus I.
Yes. Yes. You can take any complex number. All right. So how about you guys talk to your partner? If you are doing already, that's fine. Talk to your partner. Yes.
Like this.
Yes.
Find
Maybe you can log in. Sign in. Yes. You have a GitHub ID?
maybe
Yeah. Try to log in. Works. Okay, so I'm going to ask in groups. So the important thing is we share ideas, okay? Getting the correct answer is the next step. The first step is to getting the correct ideas. So I'm going to ask, how about, let's see, I did group 4. How about group 8? Okay, so who's group 8? All 4 here? Okay, so, okay, so is it yes or no? Is it basis or not? First of all, did you conclude that it's a basis? Yes, okay, so you concluded the basis. Okay, so what did you check in order to show that these consists of basis?
I tried like using but like if we assume that we want to check if some vector can be made with U1 and V2.
Okay, so you want to see that every vector in C2 can be a linear combination of U1, U2, any vector, yes. And then second,
I tried to assume that B is just any complex C2 vector.
okay. Okay, so let's put aside that how you did it. So that's the first thing you wanted to show, that any vector can be a linear combination of U1, U2. And what's the second thing you wanted to show?
So the first thing we need to show was U1 and U2 are independent.
Linearly independent. And then second thing is every vector can be linearly combinate of U1, U2. Okay, well that's, yeah, basically the two things. And you concluded these two are true. All right, so yeah, can I ask you, how did you come up with the how did you conclude the second part?
Still calculating, but just using two constant, some constant multiplied to U1 and U2 can be used to make the V, then it means that any V can be made with
Okay.
them. So
All right.
like C1, U1 plus C2, U2
Uh-huh.
equals V.
Yep. Yep. So basically what you want is finding C1, C2, satisfying this equation for any V, right? So you can write your V as this general form, and you have U1 as 1 on 1, U2 as 1 minus 1. So you want to solve for this equation, right? So you have to find C1, C2 in terms of Z1 and Z2. So if you could find the formula for C1, C2 in terms of Z1 and Z2, then it means that any complex number can be put into Z1 and Z2 to satisfy this equation. That completes the second part, right? Okay. Anyone else came up with a different approach? So the reason I put this is not only this also tightly related to our topics that we're going to cover next time on qubits, but also you can see even though I put 1 comma 1, this 1 is not the real number. It's a complex number, okay? So you have to think about every number that you see is going to be considered as a complex number. So 1 is a complex number whose imaginary part is 0, okay? And real part is 1, so on. All right, so you can work on the third part on your own. I'm not going to cover this one, but basically it's the same thing. So you can check whether this is a basis first, and then what you have to check is whether it's also normal. So normal means that each two vectors have length 1 by taking the norms, and then ortho means that they are orthogonal, they're perpendicular to each other. You can check by taking an inner product. Okay, so the next time we're going to cover the qubits. Now the real quantum computing thing happens. As I said, I'm gonna let it open. Let the live share session open until 4 p.m. If you haven't written so much by now, you can do it until 4. Meantime, I'm trying to find out the ways that I can do consistently. So Replit was my first idea, but it didn't work. So I'm keep thinking about what other services that I can use for free to let anyone can join all together and then write their own. If you have any idea what's going to be the best tool, let me know. And other than that, we'll call it here. We'll see you on Friday. And yeah, see you later. Yeah, so class over. Yes.
이익이 어느 들어가면 되는.
이게 로그인 하면 되는 것 같더라고요.
아,
로그인 했어요?
이거는
한번 중간에 물을 때가 있거든요. 이게 들어올 때.
아, 네.
어나니머스면 안 되고
아,
로그인 하면. 근데 이게 어쨌든 다른 서비스를 좀 찾기 전에는
아, 네.
이걸로 할 건데.
그리고 그 한글로 쓰면 안 되는 거죠?
뭐 써도 되긴 하는데 영어로 쓰는 게 낫지 않을까요? 이왕 연습할 겸.
로그인하면 일단은 이제 쓸 수 있어요.
네,
아,
네.
네.
로그인 해야 에디시.
제가 금요일 학회를 갔는데
네.
목금에 학회를 갔는데 금요일에 이제 이 수업 들을 수가 없었거든요.
네, 네, 네. 네, 그 동영상 올릴 테니까.
근데 거기는 뭐 출제
네, 상관없어. 네. 네.
그러면 지금 하고 있는 이 지금 쓰고 있는 거는 그 목요일에 금요일에 있는 거잖아요.
김열도 있죠.
그러면 그거는 어떻게 작성해요?
그러니까 나중에 이게 하나하나 했냐 안 했냐 하루하루 체크하는 게 아니고 다 모아가지고 한 번에 그냥 하나의 파일로 만들 거예요.
그러면
뭐
같이
학기 내내 하나도 안 했으면 아무것도 안 나오겠지만 뭔가는 할 거 아니에요. 네.
제가 이거 보면서 인디펜던트하고 베이시스 이걸 증명하는 방법이 되게 많잖아요.
예.
보통 그럼 논문에서 포멀하게 작성할 때는 어떤 식으로 작성을 하는지,
인디펜던트한 걸 보일 때요.
네, 어떻게 좀 작성되는지 여쭤볼 수 있을까요?
사실 그 과정을 적으려면은
네,
뭐 디터미넌트가 제일 디터미넌트를 하면 항상 일반적이지 않으니까 글쎄 논문에서 굳이 그거 인디펜던트를 보일 정도로 과정을 적어야 될 일이 있을까 싶긴 한데 제일 좋은 거는
네.
어쨌든
뭐 하나 0으로 만들고 남아있다 이렇게 보이는 거 뭔가 조금 수준이 낮은 것 같아가지고.
그러니까 디펜던트면은 그냥 이제 0이 되는 non-trivial combination을 찾으면 되고
네,
인디펜던트한 걸 보이려면
네,
만약에 n 차원이고 n 차원 벡터가 n 개 있으면
네,
그 n by n 벡터 행렬을 만들어서 디터미넌트 0이 아닌 걸 보이면 되고
네,
만약에 n 차원 벡터가 n보다 작은 개수만큼 모아져 있으면
네,
그게 리니얼 인디펜던트를 보이기 위해서
네.
어떤 방법을 참을 줄까? 그 이게 뭐였더라? 뭐 RREF 쓰면 되죠. 네, RREF가 제일 깔끔하겠다. 네.
N 차
아니면 랭크 계산하면 돼요. 랭크. 예, 그냥 n 개보다 적게 있으면은 이제 정방 행렬이 아니고 조금 길쭉한 행렬이 나올 거 아니에요.
네,
랭크를 계산을 해요.
네.
네.
그럼 베이시스 같은 경우는 그냥 다 이게 다
그러니까
베이시스도
베이시스는-
인디펜던트.
네, 리니어 인디펜던트 보여야 되고 그다음에 정확하게 n 개 있을 테니까
음,
네, 그냥 디터미넌트 계산하면 되죠.
그러면 모든 경우에서 보통 다 두 개에 대해서 그래서 n 개가 있으면
네.
n 마이너스 1개에 대해서
아니 여기 n 개만 하면 돼요. 우리가 이제 n 개에 대한 벡터에 대해서 한 거니까.
이해했습니다.
참고에 적으려고 하는데
예.
파일 시스템 읽기 전형이라고
로그인 하면 돼요.
로그인하면
네, 네.
볼때 그냥 수업에 디스커션하고
네, 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 네.
수업에는 모든 내용을 적어놔.
그런 건 노트를 적용한 게 아니고 그러니까 우리가 디스커션 한 거. 예.
못 들어서 그런데 내가 저기서 뭐 꼭 적어야 된다고 되게 생각한 거 그렇게 말씀하셨던 건가요?
그렇죠. 이거 우리가 지금 디스커션 한 거 있잖아요.
네.
본인이 생각했던 거 적어도 되고, 이제 디스커션 하면서 내린 결론을 적어도 되고.
시간 그런 것도 말씀하시고.
시간이? 제가 그걸 닫으면은 세션이 끊기잖아요. 일단은 4시까지 살려놓을 거거든요. 그러니까 일단 오늘은 이거 쓸 때까지는. 그러니까 우리가 VS 코드 말고 내가 원래는 레플리스 쓰려고 했는데, 그게 이제 제한이 있어가지고, 일단은 VS 코드로 임시로 하는 건데, 그거 대체할 만한 거 찾기 전까지는 그냥 제가 이거를 세션을 끄지 않는 걸로. 근데 이제 뭐 하루 이상 이렇게 할 수는 없고 좀 뒤에 몇 시간만 더 할 수 있어요. 올려서 살려놓을 수 있어요.
이거 쓸 때 수업 시간에는 배운 내용보다 디스커션 시작할 때 쓰는
네, 그런 거 써.
그걸 쓰는 거예요.
네네네네.
그리고 저거 나중에 저장만 하면 되는 건가요? 아니면 코밋도 해야 돼요?
커밋 안 해도 돼요. 커밋은 내가 할 거니까. 저장만 하면은 내 사이드에서 그냥 다 저장돼 있어.
그 코드
예.
여기서 뭘 적는 건지
그냥 그 디스커션 했던 거.
오늘 한국어
오늘
적은
한 거. 예, 예.
그 4시까지라고 했던 게
그냥 이 세션을 살려놓을 테니까 만약에 다 못 적었으면 조금 더 적어도 된다.
오늘 4시까지.
네, 네. 여기 자꾸 열리네.